Okay, now we are in chapter 7, another new topic, um, and that is actually we are talking about a specific con- uh, continuous probability distribution. Okay, so let's get started. Next slide. Um, so it's normal probability distributions. Of course, many of you may have heard about a normal probability distribution before. It is nothing but the bell curve. Okay. Now let's go to the next slide and see what's happening in this chapter. So in 7.1, we will have the introduction, and then 7.2, how do you determine normal probabilities? And then 7.3, finding values that correspond to normal probabilities. Um, and then 7.4, assessing departure from normality. Actually speaking, the first three topics are really important. We don't have to worry too much about 7.4 in this class. Okay, all right, let's go to the next slide. Okay, so now normal random variables are the most common type of continuous random variables. So now this is a normal is a continuous random variable. Now, there is some history here, who came up with the idea of a normal curve. It's a mathematician, so it's pretty old, as you can see. But nevertheless, it's still fashionable, even nowadays. The bell curve is used so much. I don't think we can do without it. Okay, all right, let's go to the next slide. So now this is a continuous probability density function, which means it is describing a continuous random variable. And remember, when you have a continuous random variable that can take any given value in a specific range, and then we talked quite clearly in chapter 5, uh, you know, um, when we talk about continuous random variables, we talk about the probability density function, not the probability mass function. Now, the probability density function, abbreviated as PDF, is like a very smooth curve, okay? And then we will use the area under the curve to calculate the probability that the random variable is in a specific range, okay? All right, so now again to sort of mention here that the normal curve is in the form of a bell. And then in the next slide we are going to look at a normal look at a random variable, which is the age of pediatrics, young children, how the ages uh, distributed, and it turns out to be normal. Now this surprises me a little bit. I could have thought that in a pediatric population you should have very young children, as well as the children in these ages like 9 to 11. But this is a little surprising. It looks like as if it belongs to a certain neighborhood where there aren't that many young moms and dads. I don't know. I mean, very young moms and dads. But in any case, uh, I was a little bit baffled by this. I don't know how you feel. So this feels as if, the infants, the probability or the proportion of infants in this population is very low, and it's mostly like the elementary school kids or elementary or middle school kids. But typically in a population, you won't get it to be disproportionate unless the neighborhood is a little bit older, right? I mean, the parents are a little bit older, maybe 30s, 40s. Okay, all right then. Um, all right, so now as we talked about, continuous random variables in the previous chapter, area under the curve is the most important one. And we talked about, that the probability that x was less than or equal to 9 was given by the darker shade. Let me actually I can talk about what's happening in here in terms of the picture. Next slide. In fact, when you read it yourself, you can look at the both slides at the same time if you have a printout or something. Um, yeah, see, what it is saying is pretty much what we talked about. Remember, we said that for a continuous random variable, probability that x is equal to a specific value is 0. Okay, in fact there should be a equal here. um, so because of that fact, it doesn't matter whether you are finding the probability that x is less than or equal to 9 or x is less than 9. Okay, here of course x is actually age. It doesn't matter. Probability that age is less than or equal to 9 and probability that age is less than 9 would be exactly the same. Okay, so that is what it is talking about. And it's also, it's like in here it says that probability that x is specifically equal to 9 is 0, and you can replace 9 by any value. Okay, all right then. So let me go to the next slide here. Yeah, so that's what was sort of discussed in the previous slide. X less than 9 or x less than or equal to 9 both have the same probability, and that is this darker shade. And then approximately it's about 40%. Okay, now how do we calculate those? The 40%, that this is 40%, it is using the the PDF equation right here. This is the PDF. PDF is usually denoted by F within parenthesis X. So the equation here is the PDF. In other words, if you think in terms of calculus, this curve is represented, the y of this curve is represented by this equation, and you have x on the x-axis or the horizontal axis. Now look in here, we'll think a little bit about this, look at this, and then let me finish this up. So how do you get this darker area, darkly shaded area? It is, if you remember calculus, you need to integrate from all the way from here up to 9. Okay, so if you put integral sign, and then now also remember a bell curve theoretically, a normal random variable theoretically can span from negative infinity, right here, negative infinity to plus infinity, theoretically. Okay, so when you have to integrate this to get that 40%, you need to integrate this starting from negative infinity up to 9. Okay, and then you will get 0.4. Okay, that's how you get that 40%. Alright, and remember, theoretically, all bell curves are going from negative infinity to plus infinity. But practically, of course, it's not the case. There are limits to most of the measurements we make in life. Okay, alright. Now let's also talk about, look at this. Look, now there is this mu and sigma which plays a role in this curve. Now mu stands for mean and sigma stands for standard deviation of this normal random variable. Okay. Now in other words, depending on the mu and the sigma, you will get lots of different kinds of curves. So you will have infinity of curves, right? Mu can be any real number, negative, positive, 0. Sigma is a positive number, right? And then both mu and sigma can be varied, and then you can generate millions and millions, infinity of normal curves. Okay, all right then, so let's go to the next one. And then yeah, let me think the next one. Yeah, so in that sense, depending on mu and sigma, you get different curves. So again, the normal PDFs are also a family of distributions, just like the way we talked about binomial distributions being a family. Depending on the mu and the sigma, you can create so many different curves, and that the whole entire collection of curves will form the family. Okay. Now again, just like in the binomial case, we said that n and p are binomial parameters. If you remember, I have written it right down in here. Just like that, for the normal curve, you have mu and sigma to be its parameters. Okay, so whenever moment you talk about a normal curve or a normal random variable, you need to ask, okay, what is the mean value? What is the standard deviation value? So these two are parameters which describes a specific curve. So if you have x to be normal, notationally we can say x is, with this sign, x is equivalent to normal with mean, mu, and sigma, standard deviation. Okay, so the first value is the mean, second value is the standard deviation. similar notation, if you remember, for binomial had x to be b, n, p. Okay, the other parameters were n and p. Here it is mu and sigma. Okay, all right. Let's go to the next slide. So remember this notation. Remember, mean comes first. Okay, so now how the curve changes according to different means. If the mean is more, 50, mean is 50, mu1 is 50, mu2 is 60, of course on the horizontal axis, mean 60 curve will be to the right. So the curve will be shifting to the right when you have larger and larger means, okay? And then what does the sigma tell us? Sigma gives us an idea about the spread of the curve. Okay. See, because sigma measures. See, if you remember, even from the empirical rule, we have like 70% coming within one standard deviation. Sigma stands for standard deviation. So, this width or the gap is actually a measurement for sigma. And look, this curve is much shorter and it is broader. So sigma 1 is larger than sigma 2. So what it is telling me is the x, or the normal random variable, which is represented by this curve, which is curve 1, is more spread out than the other one, which means this curve 1 data is less reliable, because there is a chance that it can move away from the center much more than this. So if you have sigma to be larger, that means that data is not as reliable as a data set which has a smaller sigma. So that's what I have kind of mentioned in here. I could not get the subscript. Sigma 1 is the same as this sigma 1 and sigma 2. So if you have sigma 1 to be more than sigma 2, you can see it. Then you are telling that, what it is telling you is that the curve 1 data is less reliable than curve 2, because curve 2 data has the chance of being near mu, the actual mean value, much more than curve 1 data. Okay. All right, so then let's go to the next one. So here it is just, representing the curve in terms of mu and sigma. So mu is the middle. And notice this is a symmetric distribution. And remember, way back we learned that if you have a symmetric distribution, the mean, the median, and the mode, all three measures of center are the same. Okay, for a for a normal curve, mean, median, mode are all the same. Okay, and then if the sigma is larger, you will have a shorter or a dwarfy kind of a normal curve spreading more out. Okay, all right, next. Yeah, okay. Now we need to now see, we all this time we talked about like the entire population. Lots of times, we do not have access to all the observations, which means we will be using a sample. Okay, so now what is the counterpart? What are the counterparts of mu and sigma when you talk in terms of the sample data? Okay, so you will have a sample mean and a sample standard deviation. Now we have to get familiar with the notation for that. Sample mean is x bar. Now in PowerPoint, it is very difficult to get that bar on top. Actually, this should be like x bar on top, okay? So x bar is the notation for sample mean, and S is the notation for sample standard deviation. Remember, for the population mean is mu, and population standard deviation is sigma, okay? Now also notice, samples are not the same. I can take one sample of 10 students and then look at their GPS, and then I can take another sample of 10 students. Their GPAs are not going to be exactly the same as the first sample's data. Okay, so because of that, X bar and S vary from one sample to the other. You guys agree? X bar and S vary from one sample to the other. Okay, so that means you can think of both X bar and S as random variables. They both have variability from one sample to the other. Okay, so these two are random variables. And then also let's sort of try to connect x bar and s with mean mu and sigma, which are the population parameters. Now these symbols stand for the population mean and the population standard deviation. Okay, now these are constant, they do not change. That's not like the sample, because this is based on the entire population. You are not leaving anything out. Okay, so it will be fixed. Of course, we do not know because we never can get hold of the entire population, right? So then, now actually this sample mean, sample quantity, sample mean and the sample standard deviation, and the population mean and the population standard deviation are somewhat connected. The connection is that you can estimate this unknown mean and the unknown standard deviation by a sample mean and the sample standard deviation. Okay, so that is the connection that is very important. X bar and S serve as estimates for mu and sigma. Okay, all right, so in fact we will be using this idea over and over in time to come. Okay, all right, so let's go to the next one. And now again we are visiting the empirical rule. I think there's a typo here, right? And then 68% of the curve will be between mu and sigma, 95% within two standard deviations, 99.7, which is almost all, right, will be within three standard deviations. Okay, so in fact in a figure you can see it like this. See, 68% roughly will be between mu minus sigma to mu plus sigma. Okay, likewise within two standard deviations, you will have 95% of the observations, and then almost all, or to be more specific, 99.7% of the observations will be within three standard deviations. Only a very, very few, the remaining 0.3% are outside these two little tails. Okay? All right then. So now, in fact, in this slide, that empirical rule is applied when you can take mu to be 100, sigma to be 15. If x is normal, you can say that 68% of the scores, here x is intelligence scores, 68% of the scores will be between mu plus or minus. Now this symbol stands for plus or minus. So this is actually notation for a range. Mu, see, mu minus sigma, it will be like mu minus sigma is the left boundary and mu plus sigma is the right boundary. So you get 100 minus 15 to be 85, 100 plus 15 to be 115. So what it is saying is this is a range. The left boundary is 85, right boundary is 115. So 68% of the observations fall within, within 85 and 115. Okay. Likewise, you can calculate the 95% range. 100 plus or minus twice sigma works out to 70 to 130, and then 99.7 will be between 55 to 145. So actually roughly you can estimate the maximum possible value is like 145 because almost all the observations are below this. Okay, and the minimum value for this data, the intelligence scores, is 55 in this sample, right? So the scores completely, if you take the whole data set, have been ranging from 55 to 145 with an average of 100. Okay, all right then, so let's go to the next one. Okay, so symmetry in the tails, the curve is symmetric. Normal curve is really symmetric. That is a very, very important feature. We are going to use it a lot. Okay, and then because of we can, because the normal curve is symmetrical uh, and the total AUC adds to 1, right? So because that the one half, half of the curve is 0.5 and the other half is 0.5, and the behavior of the curve on either side, on both sides, are pretty much the same, right? So if you talk about 95%, okay, so let me go back in here. 95% will be between these two. Now, because the curve is symmetric, so the remaining 5% you can equally divide between the two tails. Okay, so 95 will be in the middle. The remaining 5% is equally divided. This part will have 2.5% and this part will have 2.5. 2.5 plus 2.5 will add to 5%, right? Okay, so let's go to the next one. Yeah, I think we talked about that. Um, yeah, so that's, yeah, in fact, in this picture, that's what they're showing, right? Because the curve is symmetric, only you can do this. You can equally divide because the curve is symmetric. Okay, so now, so here's another example. The male height is approximately normal with mean 70 and a sigma 2.8. Now, because of that empirical rule, or 68, 95, 99.7 rule, 68% of the population will be between, will have heights between these two measurements, right? 67.2 inches to 72.8 inches. And then, um, so 68 means 32% will be outside this range. So 32% will be out, like either below 67.2 or higher than 72.8. Now, if you take exact half of 32%, 16% will be below 67.2 and the remaining 16% will be above 72.8. Okay, so it's the same idea. Now, like in this situation, now the same idea can be applied even for the 68% range. Okay. Okay, so that we did. So yeah, we'll not worry about this. This is about inflection points. We don't have to worry about that. If you are concerned, you can talk to me. Um, mm, Yeah, now see, this again will not worry about this. What it is saying is, now this is an important feature, but you may learn this in a higher biostat class. Lots of times, or not lots of times, good amount of biostatistical data, uh, maybe not normal. Okay, then you can do transformations like logarithms. Instead of working with y, you can work with logarithm, and logarithm of y will be normal. You can square root. So now this is an important thing, but nevertheless, we are not going to worry about this. But keep in mind, if you do a higher level stat class or something, definitely you'll go over this in more detail. In other words, some of the non-normal variables can be made to be normal by means of a transformation. Okay. Okay. So yeah, see now that this is this slide is talking about logarithms, um, but which you may know even from your college algebra. It's just a review if you want to go over it. But as far as this class goes, you don't have to know logarithms. But nevertheless, for science majors, logs are quite important, right, in chemistry and so forth. Okay, so you don't have to worry about this slide. Um, I'll just say skip, okay, because transformations we are not going to worry about. But sometimes we always like to learn more than what is expected. So when you have the time, you can go over these slides, okay? Okay. Yeah, now this is the next thing. Okay, this is important. So now we talked about the normal probability distribution. We got an idea. So in section 7.2, we are going to talk about how do you calculate normal probabilities. Now remember, I said that there are millions of normal curves because depending on the mean and the sigma. But so how do you calculate normal probabilities? But see, lots of times people look up a normal tables. There should be some standard. So there is a way of standardizing. In fact, if you take x minus mu divided by sigma, where x is a normal random variable, and then you create this new random variable z, then this z is actually, this is really neat, this z is normal with mean 0 and standard deviation 1. How about that? So Z is normal with mean 0 and standard 1. And okay, and Z is called, in fact, standard normal random variable. It is given a special name because it's so important. If you have a random variable to be with mean 0 and standard deviation 1, we give that special notation Z to denote it, and then it is also called a standard normal random variable. So given any normal random variable x, we can create a standard normal random variable by doing x minus mu over sigma. Actually, z values are called z-scores. I'm sure you guys have come across this before, z-scores, right? So it's really important. All right, let's go to the next one. So now here, there's an example here. They are saying that, okay, we want to determine the percentage of human gestations that are less than 40 weeks in length. Okay, that means pregnancy period. Now they say that human pregnancy on the average is 39 weeks and with a standard deviation of 2, and you can expect the human pregnancy period to be approximately normal. Okay, so that's what it is saying here. And then we will represent x to be the human gestation period. That means how long the mother is pregnant. And then the mean will be 39 weeks with a standard deviation of 2. Now you need to say you are curious to know, okay, what is the probability that the gestation period will be less than or equal to 40? Okay, remember this is just the mean. This is just halfway of the curve. Okay, so how do you find this? Okay, so that is a question in normal probability. So let's see how that works. Okay, so so we create the standard normal random variable. Okay, and then now the probabilities or the cumulative probabilities for standard normal are available either in textbooks, almost every stat book has at the end, or you can use software to calculate this. Okay, so let's see now. In fact, this book has at the end table B. So let's look in here. Here's see, these are the probabilities. These 4-digit numbers are these areas, okay, up to a certain value of the standard normal Z. So since the Z is standard normal, the mean is 0. Okay, so the mean is 0 and then standard deviation is 1. So if you want to find, like, okay, Z, now here what they have done is, okay, they are illustrating to you what is the probability that Z is less than 1.96. See, this is like the Z axis. What is the probability that Z is less than 1.96, right? Less than or equal to is the same, right? And then what you do is you go to the table. Now, right on the leftmost column, you will find Z up to the first decimal place. And the second decimal place, the 6, you can find right on top. So 1.96. So if you just get the meeting point of this row and the column, you will find the probability or the area under this curve. Area under the curve is the same as the probability. So probability that x is less than or equal to 1.96 is 0.975, 97.5%, right? In other words, the standard normal 97.5% of the standard normal random variables will be less than 1.96. Okay, so just take a look at it. So the up to the first decimal of the z-score will be here. The second one, you need to go along that row and then get the meeting point to find the probability or the area under the curve, which are the same. Okay. All right. So let's so these so it's just showing how to do a problem. You first find the z-score, and then you will find the you now see to find x less than 40. Let's see, yes, x less than 40, you find the z-score for x. So you plug 40, mean was 39 weeks, remember, standard deviation was 2. So for x equal to 40, the z-score is 0.5. So if you want to find the probability that x is less than 40, it's the same as probability that z is less than 0.5. Okay. In fact, I can write it in here. Probability that x is less than, right? Less than 40. That's what you wanted to find. Remember, x is the gestation period. Now that is the same as probability that z. See, we found the z-score for 40, and then it turned out to be 0.5. Okay. So now this you can find from those tables in the previous slide, right? Or in the at the back of your book. And then once you find this, you have found this. Okay. So 0.5 is right here. I mean, you don't need the second decimal place because it's 0. And then you can see it's 0.6915. So what it is telling is about 69.15% of the pregnancies have a gestation period of less than 40. Okay, that's what it is saying, right? That is the practical interpretation, right? So so let's go to the next one. So likewise, you can find the probabilities for all kinds of ranges. So here you have a to be less than a is less than b, and if you want to find the probability that z is between a and b, it is expressed in this. Okay. So what you might want to do is how do you find this? You first look for the probability for z equal to a from the table, then look for the probability for z equal to b, then you subtract, right? Because z equal to b will be all the way from negative infinity up to here. Z equal to a probability will be only this part. So if you need this, you subtract the smaller part from the larger one to get the in between. Okay, so that's pretty much what you need to do if you have a range like this. So that's what is explained here. Okay. Excuse me. So when you do a couple of problems, you get the idea what to do. It's really not a big deal at all. Okay. So it's just here in form of steps. They have now the other way. See, all this time, let me go back here. All this time we knew the x value to begin with. From the x we knew the z. That means we knew the range for the horizontal axis, and then we found this. Okay. Now if you know this, how will you find this? That is the next thing. In fact, if you know something like this, what is this? If this is like, let's say, if this is like 60.6, what is this? This is the 60th percentile, right? Because 60% of the observations are less than this value. We talked about percentiles before. So in other words, how do you find percentiles? It is the other way around. You are given the percentile value. You need to find, you are given the percentage value, then you have to find the percentile. Okay, it's the opposite. So let's see how that works. Let's see. So we went here. Yeah, okay, right here. So actually finding values corresponding to normal probabilities. Actually, these are finding values. These are percentiles. Okay. Percentiles. Actually, they are also called quantiles, but the more commonly used one is percentiles, but the more correct one is quantiles. Quantiles. Okay, let's see. Let me first reduce the size here a little bit. Okay. So, in fact, it's the zth percentile. So to find that, this is all you do. See, this is just algebra. Remember z was x minus mu over sigma. You just manipulate that equation and then just bring x over to the left hand side, and then you have this on the right hand side. You will know mu, you will know sigma. Okay, then you can find ZP. This is the pth percentile for the standard normal. And then you can get the X. Okay, so that's all there is. So you first find this from the table, and then you use this little algebra to get the X value. Remember, Z's are standard normal. Always they have mean 0 and standard deviation 1. X is the random variable that we are interested in. Okay, once you find this, you have to go back and then find this. Let's see in the next slide. um, yeah, now when you do this, of course, it is the opposite. See, let me go back to this. Uh, Now see, if you have something like 95%, if you look in this table, you will not find 95% exactly. See, you will have let's see, 94.41, 95.45, 90. So you don't get exactly 95. So what you have to search for is approximate value, and then get the z which corresponds to that which corresponds to that probability. In other words, if this is p, this is like zp. Okay, you need to do some problems, of course, to sort of be more comfortable with this. But once you do a couple of problems, it's really not a big deal at all. So that's what this slide is telling, to approximate, because you won't get the exact value. Okay. Yeah, see, suppose you want to, here, this is a slide, this explains the whole thing. Suppose you want the 97.5th percentile of the z-score. So this whole curve is, up to this point, is 0.975. So what you do is you go and search these 4 digits. These are the areas or the probabilities. So you search all over and see where about is 0.975. So not yet here. So go in here, and then somewhere here, of course, you get exactly 0.97. That's very rare to get the exact value. Nevertheless, now what you need to do is you have to find the z, which is the opposite of what we did. So now you go back here. Okay, so up to the first decimal place, it is 1.9, and the second decimal place is 6, so we'll have 1.96. So this is the 97.5th percentile, and this is how you express it. Okay, this is like your p value. Okay, see, this p is 0.975. And then if you want to go one more step and get the x, then you will use mu plus z sigma. Okay. Okay, so now um, um, yeah, suppose we want to know what gestational length is less than 97.5% of all the gestations. So you have x to be with mean 39, standard deviation 2. Then the 97.5th percentile we found was 1.96, right? Um, and then and then in order to get that, let's see how this works. So okay, yeah, let me go back to this slide. I sort of had to pause a little here. Now here's another example where you use the percentile idea. Okay, now say you want to know what gestational length is less than 97.5 of all gestations. So in other words, what is the gestation length that is shorter than 0.975 of all gestations? Actually, it's easier to visualize it using this curve. See, we are looking for the gestational length which is shorter than 97.5% of them, which means it is this part, right? So in other words, you need to find this value. So we know that, okay, the proportion which is less than 97.5% would be 0.025. So we know 0.025. We will go to the standard normal, and then we will look and find the 4-digit 0.025, and then go back and then look for the z-score up to the first decimal place here, and then add it on to the second decimal place to get negative 1.96. In fact, the entire tables, you will have negative numbers as well. Okay, a good idea would be to go over this problem with your table spread out, and then then you will understand this. So now at this point, so you have found z. Now the next is to find the actual x value. What is the gestational period which is shorter than 97.5% of them? So you need to use that x equals mu plus sigma z, which is used here. See, this is your mu value, this is your sigma value, this is your I'm sorry, this is your mu value, this is your z value, and this is your sigma value. So in other words, this is the 2.5th. See, this is the 2.5th percentile of the gestation period. Okay, and that is 35 weeks, right? All right. So percentiles are also important, and to find the percentiles, the proportion or the probability, then you find this. Typically, you first find the z-score corresponding to that percentage or the proportion, and then you make the transformation or conversion to x using this equation. In fact, the book uses the term unstandardizing. Okay, now this again, you don't have to, you're not responsible for this. Just extra. I'll just say extra. Okay. Again, assessing departures from normality. This is important. Like if you do higher stat classes, of course, when you do like consulting work or in projects and things like that, this will be very, very useful. Okay, because if you are to use normal probability theory, you need to figure out whether the random variable that you're talking about or working with is normal. Okay, so you first have to see, okay, is it normal? How far away is it normal? So in order to do that, in a very simple way, you can look at the histogram. We know about histogram, right? If the histogram is not symmetric, if it is not a bell shape, then then the data is not normal. I'm sorry. Okay. So I mean, as far as this class is concerned, only knowing the histogram is enough. But QQ plots, those are pretty interesting stuff. If you have the time, once this course is over, you can read about it. But even during the course, if you are interested, certainly you can contact me. But you're not responsible for this as far as tests and other assignments go. Okay. Yeah, so this is here's the histogram. This is like a QQ plot, and then if the QQ, once you have the QQ plot, if you have all the data on that line, on like a diagonal line, then that means the data is normal. Okay, so this is here, it is not normal. So these slides give like different situations where the data are not normal, so that you can use these as references. Okay. All right, so this is the end of the normal probability distribution presentation. This is an important topic, and then it's interesting too, so we need to do some problems and then get going. Okay, so actually speaking, to summarize what you need to know, you need to know how to find the probabilities, right, for the for a given range. You need to know how to find the z-score, and then you need to know how to find the percentiles. Okay, so those are the stat side of things. But once you read a word problem, you need to be able to sort of relate to each variable in the problem, to the x value, the mean value, standard deviation, and so forth. So you need to get some experience with it. Okay, So I'm going to stop here. Take care. And if you have any questions, please email me or post. Okay.